In the last slide, we discussed isotropic hardening. In isotropic hardening, the loading was monotonic, or increases without reversal. If the hardening of the material takes place due to cyclic loading, it is known as a kinematic hardening. Consider a steel specimen loaded with a cyclic load, as shown in the figure. The graph on the right-hand side shows the hysteresis of stress versus plastic deformation. As the specimen is loaded, initially the plastic deformation is 0. As the load increases, causing the stress to increase beyond the yield strength of the material, the plastic deformation takes place. After reaching the peak load, the load is reversed. With load reversal, initially, the elastic strain will be relieved, and the specimen will come to a zero stress state, with plastic deformation retained in it. As the load further increases, in the opposite direction, the specimen will accumulate elastic deformation in the other direction. After reaching the yield stress, the plastic deformation will begin to take place. As the load and hence the plastic deformation is in the opposite direction, plastic deformation accumulated in the previous half of the loading cycles will reduce. Finally, the specimen will come to a zero plastic strain condition. The specimen will still have a compressive stress. Peak load, in the opposite direction, will have the peak plastic deformation in the opposite direction. As the load is reversed again, elastic strain accumulated will be relieved, and the component will again come to zero stress with plastic deformation state. This time, the deformation, and hence the strain direction, will be the opposite. As more such load reversal cycles are applied, more such stress deformation cycles will be accumulated. In the last slide, we saw a cyclic loading applied on the specimen. This slide shows the plastic strain in the tensile and the compressive direction, plotted as a function of number of load reversal cycles. The first graph shows a tensile plastic strain versus the number of load reversal cycles. As we can note, the plastic strain goes on reducing with increase in the load reversal cycles. This indicates that lesser plastic strain is developed with the same level of applied load or stress. Thus, the specimen hardens in the tensile direction. The second graph shows the compressive plastic strain versus the number of load reversal cycles. As we can note, the compressive plastic strain goes on increasing with increase in the load reversal cycles. This indicates that a larger plastic strain is developed with the same level of applied load or stress. Thus, the specimen softens in the compressive direction. This behavior is known as the kinematic hardening. It is a non-isotropic response of a material due to cyclic loading. The material hardens in one direction and softens in the opposite direction. In terms of a cylindrical yield surface, the yield surface moves in one direction. This movement, or offset, can be towards the tensile end, or towards the compressive end.